Welcome back to the Aero Guy. In today's episode, we'll tackle some practice problems involving the International Standard Atmosphere, or ISA, an essential concept for aeronautical engineers and pilots alike. And at the end, we'll throw in some tricky bonus questions, so stay tuned. And for our first problem today, we'll calculate standard atmospheric values using what we learned in the previous videos. If you haven't watched them yet, go check them out. With that knowledge, we can determine standard temperature, pressure, and density using the formulas we derived, or even by using the ISA table we generated from those formulas. So the question is asking us to calculate the standard atmospheric values of temperature, pressure, and density at a geopotential altitude of 14 kilometers. So let's go over in solving this problem using the first method, and that is to use the ISA table. What I have here is the ISA table generated or taken from John Anderson's book Introduction to Flight from Appendix A. As you can see, there are 4 columns representing altitude, temperature, pressure, and density. And altitude is further subdivided into 2 columns, and that is your geometric altitude and your geopotential altitude. Looking at the data, we only have 14 kilometers as geometric altitude. Its counterpart, the geopotential altitude of 13,969 meters. Using this table, we are able to get temperature and pressure and density to be of the following data. But again, this is only for a geopotential altitude of 13,969 meters, close to 14 kilometers. We can get an exact value simply by using this table, by interpolation, by using equations of a line, finding the slope. However, we have a more accurate way to solve it. That is by using method number 2. Method number 2 is solving for the values. And again, we're being tasked to solve for temperature, pressure, and density, a geopotential altitude of 14 kilometers. 14 kilometers falls within the 11 to 25 kilometer range for the tropopause, which is an isothermal region. Therefore, temperature is a constant at 216.66 Kelvin. Therefore, temperature at 14 kilometers is 216.66 Kelvin. As for pressure, since we are at the isothermal region of the atmosphere, we can use the isothermal properties or formulas that we have derived from the previous videos. For pressure, the pressure ratio formula is given by this equation. Simplifying the equation, we're looking for pressure 2, and that is pressure at 14 kilometers. There is a problem here, however. We do not know the value of P1. We cannot use the value at sea level because there has been a change in temperature from sea level to 11 kilometers. Therefore, what we can use is the 11 kilometer pressure. Hence, we need to solve for that one using the known equations we have for the gradient region. So we will pause this equation first for now, and we will use a different equation just to solve for the pressure at 11 kilometers. And that is your pressure ratio at the gradient region, P2 over P1 is equal to temperature change. And just defining each variable, we are defining P2 as P11 at this point and defining P1 as P sea level. And substituting the knowns. Working further into this problem, rewriting the equation. We get, by substituting the knowns, the values here serving as the exponent can be simplified. As 5.26. Try that in your calculators. And with that, we can solve for the pressure at 11 kilometers to be as this value. Since we now have a value for the pressure at 11 kilometers, we can solve for the pressure at 14 kilometers, given the formula that we parked earlier. Continuing the equation that we parked earlier, to solve for the pressure at 14 kilometers, we will use again the isothermal pressure ratio formula. So allow me to copy that formula here, paste it, changing the variables into what we're actually looking for. We're looking for 14 kilometers. 11 kilometers is already solved. We already have height 2, which is 14 kilometers, and height 1 is your 11 kilometers. And using our calculator here, we get our final answer to be at 14,087.039 pascals. And as for density, we'll still use the same approach that we did earlier for pressure. That is by using the density ratio in an isothermal region. However, we still do not know the density at 11 kilometers, representing our density 1 on the equation. So we need to solve for the density at 11 kilometers by using the density ratio at the gradient region. We already derived the formula for that one, and you can simplify the exponent by solving for it already, so that you won't need to memorize the equations always. You just have to solve for the exponent already, and that is represented by 4.26, or that is equal to 4.26. So with that, substitute the knowns. You have your density at sea level, that is already a known. That's 1.225 kilogram per cubic meter for the SI units. And we already have temperature 2 and temperature 1 to be at their respective values. So with that, density at 11 kilometers is 0.367 kilogram per cubic meter. Substituting that into the equation for the density ratio at the isothermal region, again we're looking for the density at 14 kilometers. We will use the appropriate equation. Substituting the knowns, density at 11 kilometers, gravity at sea level, the gas constant for air, temperature at 11 kilometers, and the altitudes that we are comparing data, which is your 14,000 meters or 14 kilometers and your 11,000 meters or your 11 kilometers, giving you the final value for density at 14 kilometers to be at 0.23 kilograms per cubic meter. That's all for problem number 1. For our second problem, if an airplane is flying at an altitude where the actual pressure and temperature are 4.72 times 10 raised to the power of 4 pascals and 255.7 Kelvin, respectively, what are the pressure, temperature, and density altitudes? In this problem, we are being tasked to solve for the corresponding altitudes for the given values for pressure, temperature, and as well as density. Density may not be given here, but it is solvable. Without further ado, let's approach this problem. Let's try to solve for temperature first. Temperature is given as 255.7 Kelvin. That is greater than your 216.66 Kelvin temperature at the tropopause, meaning this value could be at the troposphere or it could be at the exosphere. However, again, an airplane is flying at that altitude. No airplane can fly at the exosphere. Therefore, this temperature only means that we are within the troposphere. So, solving for temperature, we understood that this value is just within the troposphere, and we can use the temperature lapse rate equation to determine the height corresponding to such temperature. By deriving an equation from the lapse rate equation, we get height is equal to temperature at the altitude minus temperature 1, and that is your sea level, divided by the lapse rate value plus height 1. And with that, we are able to solve for the height corresponding to such temperature to be at 4,993.846 meters. And that is your temperature altitude for this temperature. And as for pressure altitude, since we are already given the value of pressure at that altitude, we may be able to use the pressure ratio formula at the troposphere to determine temperature at that altitude given the value of pressure at that altitude, and then substitute it later to the temperature lapse rate equation that is derived to solve for height. So, without further ado, let's start with step 1, that is to solve for the temperature given the pressure at that altitude, giving you a temperature of 249.206 Kelvin. Substituting this into the lapse rate equation that has been derived or that has been rearranged to solve for the height at a certain temperature. This gives you a value of 5,992.907 meters. And solving for density altitude, there is one slight problem. We do not have the value of density at that altitude. However, we can solve for that one using the formula we know as the equation of state. And in solving this problem, in solving for the density altitude, the approach is similar to solving for the pressure altitude. We still need to determine the temperature at that altitude and then solve for the height using that temperature. But again, we do not know the value of density at that altitude. So using the equation of state, Solving for density, you get a density of 0.642996 kilogram per cubic meter. And substituting that into this equation, we get a temperature of 247.698 Kelvin. And substituting this temperature to this formula, which is used to solve for the height corresponding to that temperature, we get 6224.883 meters. And that is now your density altitude. In our problem, we calculated altitude using standard formulas, but the values for pressure, temperature, and density altitude differ simply because they depend on different factors. This is why the same altitude can never have the same values for pressure, density, and temperature, and all of these values impact aircraft performance. And let us now move on to our bonus problem. The first one is literally an out of this world problem. Now, on the first approach, you might find this intimidating, but reading the problem again and again allows you to figure out some clues. The problem goes like this. The atmosphere of Jupiter is essentially made up of hydrogen, H2. For H2, the specific gas constant is 4157 joules per kilogram per Kelvin. The acceleration of gravity of Jupiter is 24.9 meters per second squared, and assuming an isothermal atmosphere with a temperature of 150 Kelvin, and assuming that Jupiter has a definable surface, calculate the altitude above that surface, where the pressure is 1/2 of the surface pressure. This time, let's look into some context clues. We are already given that we are in Jupiter. Its atmosphere is different as that of Earth. It's made up of hydrogen. Therefore, the gas constant is different. Gravity is also different. And the problem is also stating that Jupiter has an isothermal atmosphere, meaning there is no change in temperature from the lower altitude to a higher altitude. Let me highlight that part. Isothermal atmosphere with a constant temperature of 150 Kelvin. And it's also telling us that Jupiter has a definable surface. Although it's a gas planet, Jupiter has a definable surface. So it's asking us to calculate the altitude above the surface where the pressure is just 1/2 of the pressure at the surface. So again, this is a straightforward problem. So now let's approach this problem. It's asking us to solve for the altitude to which the pressure is just 1/2 of the surface pressure. It's just simply asking us for the altitude value. And to approach that, we need to understand that we are already at the isothermal region of the atmosphere, of Jupiter's atmosphere. And we already have an equation for the isothermal region. That is pressure 2, pressure 1 is equal to this value. We already know pressure 2, that's just 1/2 of pressure 1. And we already know the gravity of Jupiter, assuming that it does not change, it's a constant value. We already know the gas constant. We already know the temperature. We're looking for that height, and we already know the height at the surface, which is just 0. So just defining pressure 2 to just equal to just 1/2 of pressure 1, we can just substitute that into this part of the equation. So that's just 1/2 of pressure 1 divided by pressure 1 is equal to this value. Canceling out pressure 1, we get a further simplified equation. And further simplifying the equation, we get, we're looking for that height, let me define it as hx, minus the height of the surface, which is just the same as defining it as the height at sea level. And the value is just 0, giving you this equation. And by applying algebra, applying the natural logarithm just to further simplify the equation, we now have a simplified equation to determine the height. There you have it. And substituting the knowns in our equation and canceling out the negative signs, in putting this in our calculators, gas constant in Jupiter for hydrogen is 4157 times 150 Kelvin divided by gravity of 24.9. We get the altitude to be at 17,357.91 meters. That's 17 kilometers. Our last problem, assume that you're ascending in an elevator at sea level. Your eardrums are very sensitive to minute changes in pressure. In this case, you're feeling a 1% decrease in pressure per minute. Calculate the upward speed of the elevator in meters per minute. This problem is on face value a bit difficult, but if you dive deeper into the problem itself, you'll figure out that this is just a problem using the hydrostatic equation and a little bit of background in calculus. To solve this problem, we need an equation that relates pressure with altitude, and we have a basic equation for that one, and that is your hydrostatic equation, which relates pressure with altitude. Right? And this problem is already asking us to solve for the upward speed, meaning how much distance does it cover with time? How much distance does the elevator cover with time? We can just derive the equation, express it in terms of change in time. That's change in pressure per change in time, giving you change in height per change in time. Rearranging the equation, we get an equation that gives us the change in height per change in time, given as change in pressure per change in time divided by density multiplied by gravity. And this change in pressure per change in time is already given. The problem stated that you are feeling a 1% decrease in pressure per minute. That's your 1% decrease, 0.01 from sea level. That's 101,325. Right? divided by your density to be at 1.225 and your gravity to be at 9.8066 negative value. So using our calculators, substituting the known values, we get the final value or change in height per time to be at 84,345,528,23026 meters per minute. There you have it. The change in height per time. In this video, we solved problems involving the ISA and tackled bonus problems like an out-of-this-world problem involving Jupiter's isothermal atmosphere. We also did an elevator problem using the hydrostatic equation. And I hope this helps in applying what we learned about the atmosphere. If you found this helpful, please like, subscribe, and share it with your friends. And remember, attitude defines heading, speed, and altitude. Thank you.